This is Dr. Kraus, and I guess I've already done a frequency response video, but I'm calling this Bode Part 1, Overview and Sketching, although I'm going to use the terms Bode plot and frequency response pretty much interchangeably. So these are the topics that I want to cover in the next few videos on Bode plots. I want to talk about how to sketch them by hand. I want to talk about how to generate them using using Python, and you don't necessarily kind of need the Python control module, but we're going to use the Python control module to do that. Then I want to talk about how to interpret Bode plots and use them for system ID, how to run swept sign experiments and generate Bode plots for experimental data. We'll have to talk a little bit about what the FFT is and how you generate the frequency vector to go with your FFT. And then there's already a YouTube video from last year's course on a random Bode problem generator, but I want to revisit that and see if I want to make any updates to that and just show students how to use it. And then we'll conclude with some kind of experimental example. So why do I think it's important for you to learn how to sketch Bode plots by hand, particularly when computers can generate them automatically? I think my students can anticipate some kind of comment about me being old and grumpy and not trusting computers. But I think the bigger issue is a couple of things. One, it really doesn't take that much effort to learn how to sketch Bode plots. Once you know how to sketch them by hand, you can easily kind of sketch them in your head, and that will allow you to quickly double check something that's coming out of a computer in case somebody's made a typo in the transfer function or something. And it will drive you to a deeper understanding of Bode plots to have to sketch them, and then that will in turn make it easier for you to interpret them when you're trying to do system identification. So for all of those reasons, I'm going to expect my students to know how to sketch Bode plots by hand, and that will be a subject of quizzes and tests coming up. So it really isn't that hard. The main issue, we talked in class last time about the 6 building blocks of transfer functions: pure integrators, pure differentiators, first order poles, first order zeros, second order poles, and second order zeros. If you understand how each of those 6 things affects a Bode plot, then you can easily take a transfer function, break it into its poles and zeros, and then figure out how to sketch its Bode plot from there. So just kind of algorithmic thinking about this, basically you go from low frequency to high frequency. So that means you start at very low frequency and ask yourself, does my transfer function have a pure integrator or a pure differentiator? If so, that dictates the initial slope and initial phase of your transfer function. If not, then there will be a finite value if you plug in s equal to 0. Doing so will allow you to calculate the low frequency magnitude that would intercept the y-axis of your dB magnitude plot. And then you just basically move up in frequency until you come to the next polar 0, and then at each polar 0, you figure out what type. We're talking first order, second order, and then is it a 0 or a pole, and make the appropriate adjustments to the slope of your magnitude and the phase, just the value of your phase, and that's kind of all that it takes. So let's get started with the first of our 6 building blocks. Let's talk about the pure integrator. So if I'm trying to sketch a Bode plot for a pure integrator, then what I mean is that g of s is simply 1 over s. Now, whenever we plot a Bode plot, we are simply going to substitute in s is equal to j omega. So j omega would simply be 1 over j omega. So 2 things about that at this point. One, we're going to talk about magnitude and phase. It's sort of like taking the transfer function and converting it to polar form. So we need to be able to extract that magnitude and phase separately. That means we're going to think a lot in terms of what a particular point would look like on a real versus imaginary axis. And so if I had some point out here, it would have some magnitude and some phase. So we're trying to get to that. The other thing about that is when I'm trying to determine magnitude and phase, especially phase, it really doesn't go well to have a j in the denominator. So we're always going to want to multiply by the complex conjugate or something, numerator and denominator. And that would make, so in this case, we could do complex conjugate, which would be negative j omega. Since it's just 1 over j omega, I'm just going to multiply by j over j. Yeah, I don't know if the complex conjugate would be better or worse. I'm going to have a negative sign I'm going to have to factor out anyways. So I'm multiplying by essentially 1 here, right? Something in the numerator matching something in the denominator. So I get a j over a negative omega, just a negative omega. But then I got this negative sign in the denominator, so that's kind of annoying. So I'm going to pull that up top. And so what we're saying is that for a pure integrator, j omega is a negative j divided by omega. What does that mean? And so we're basically now trying to, a Bode plot is representing the magnitude and phase of this over a range of omega. So we want omega to go from something small to something large. And to some degree, it's up to us to pick a range that makes sense here. Since we've got an omega in the denominator, by itself, when I plug in omega equal to 0, this would go off to infinity, which is a characteristic of a pure integrator. And then as omega gets large, this is going to go to 0. But if we come back to this real versus imaginary plot, it's always purely imaginary, and it's always on the negative axis. So it's starting off somewhere far away in terms of, because it's got a large magnitude for small omega. And then as omega gets larger, we eventually walk our way up here. So we're always negative. If we think about the phase angle to one of these points, our phi is always minus 90 degrees. And like I said, our magnitude would be infinite for really, really, really small omega, or omega equal to 0. And then it's going to get smaller and smaller and smaller and smaller. So, and the phase, like I said, will always be negative 90 for all omegas. So let's talk a little bit more specifically about the magnitude as a function of omega. So if I chose, for example, omega equal to 1, 10, 100, 1000, then the magnitude of j omega, that magnitude would actually just equal 1 over omega. So this is 1, 0.1, 0.01, 0.001. So you can see that for every factor of 10 increase in omega, I've got a factor of 10 decrease in the magnitude of j omega. Not surprising. Now, somewhat for historical reasons, but also because it makes Bode plots easy to sketch, we're going to have a log scale on our y-axis. That's going to become, because we're going to use a decibel. Now, a decibel is 20 log 10 of the magnitude of j omega. So 10 to what power is a 1? Well, that's a 0. And then 0 times 20 is just 0. 10 to what? So what's the log 10 of 0.1? Well, that's a negative 1. 10 to the negative 1 is equal to 0.1. 20 times that makes this a negative 20. Similarly, this is 10 to the negative 2. So a negative 2 times 20 is a negative 40. This is 10 to the negative third, so the log of that is negative 3 times that, so this is negative 60. So in Bode plot terms, we refer to this as a magnitude that is decreasing at 20 dB per decade. So we say that we have a slope for our magnitude plot of a minus 20 dB per decade. I've kind of written that terribly. So dB per decade, where decade refers to a factor of 10 increase in our frequency. So at that point, I would say that we're ready to sketch the Bode plot for a pure integrator. And what we're saying is that if we had a dB magnitude that started at, well, it's not really going to start at 0. It's going to have a slope wherever it starts of minus 20 dB per decade. It's actually going to go off to infinity, and then the phase portion is going to just always be a constant negative 90 degrees. And so that's always the phase. I guess we could say if we had a 0 dB line, the way that we've drawn this, this would correspond to omega equal to 1. Now, unfortunately, that's in radians per second, so that's just a little weird. I would never use radians per second on the frequency axis, so I got to convert that to hertz. So slightly awkwardly, that becomes a 1 over 2 pi hertz. Nevertheless, I've got a Bode plot. It's got a minus 20 dB per second slope, minus 90 degrees constant phase, and this is legitimately a Bode plot for G is equal to 1 over S. So the next step is to go in and just keep moving along in understanding. So if you have a Bode transfer function that has a pure integrator, then at low frequencies, you've got to start with a minus 20 dB per decade slope. Your magnitude has to go off to positive infinity, and your phase has to start at minus 90. Now, next building block, when we talk about a pure differentiator, so building block number 2, G is just equal to S. Basically, a 0 has the opposite effect of a Bode on the Bode plot as the corresponding pole. So not surprisingly, this would just be that G of j omega is simply equal to j omega. So now every time if I had omega versus the magnitude of G j omega, these are actually the same. So this is just 1, 1, 10, 10, 100, 100, 1000, 1000, or 0 plus 20 dB plus 40 dB plus 60 dB. So it's a positive 20 dB per decade slope. And if you think about drawing this on a real versus imaginary axis, it starts out here for omega equal to 0, and then as omega is increasing, it marches out along that axis, but it's always purely imaginary and it's always positive. So the slope is always a plus 90 dB per decade. So if I had a dB magnitude and a phase for my pure differentiator, it's going to go up with a slope of plus 20 dB per decade, and the phase would just always be a constant plus 90 degrees. So if I have a transfer function that has a pure differentiator, my Bode plot goes to negative infinity in magnitude for omega equal to 0. Because if I'm trying to get 10 to what power is actually equal to 0, well, the answer to that is negative infinity. But then my slope goes up at plus 20 dB per decade, and my phase starts at plus 90. So like I said, the first step in our algorithm, do you have a pure integrator, do you have a pure differentiator, or neither? And that determines your initial slope and your initial phase. Coincidentally, if you have neither of these things, then your initial slope is 0, flat, and your initial phase is 0 degrees. Okay, so next, let's consider our second of the I guess this is the third building block of transfer functions, the first order pole. By that, I mean that G of S is equal to P over S plus P. And this is part of where the idea that we use maybe I haven't said this explicitly, we're going to have a semi-log axis on our x-axis, our frequency axis, and then we're also using dB magnitude to give the logarithmic, to make our y-axis logarithmic. That's going to allow us to separate this into two straight line sections. So we want to consider two of regions, S much, much less than P, and S much, much greater than P. So S approaching 0 and S approaching infinity, we'll draw a straight line asymptote for region low frequency region, high frequency region, and then we'll kind of fudge what happens near the intersection, and we'll end up with a pretty good approximation of the Bode plot over the entire frequency range. So let's start with S much, much less than P. I guess for no particularly good reason, I'm going to call this region 1 low frequency. If that's true, then J omega for S much, much less than P would approximately become just P over P. Well, that's exactly 1, but more specifically, more generally, it's a constant, a real, completely real constant, and in our case, a positive real constant. So that would put it over here on our real versus imaginary axis. And so phi is initially equal to 0 for these low frequencies. And if we don't have any gain term, and it really is just P over P, then this is just 0 dB, right? Because again, we're saying what's 20 log 10 of 1? Well, 10 to the 0 power is 1, so this is 0, and then 0 times 20 is 0. So the low frequency region of our dB magnitude has a slope of 0 and a magnitude of 0 dB, and our phase also starts at 0 degrees. Okay, so then that's going to be my asymptote, and I'm going to say that's what's happening up until omega is equal to P, or F is equal to P over 2 pi. Here I am. Now what happens for region 2? S is much, much greater than P. Or omega is much, much greater than P. Either way, you want to think about that. So now J omega would be P, well, approximately P over J omega. We basically said that the S magnitude or the J omega magnitude is much, much greater than P, so I'm ignoring the other P in my denominator. I'm going to multiply through by negative J over negative J. I'll get J squared, which is negative, which will cancel the negative. And so we're saying that J omega for large S, or large omega, is approximately a negative Pj over omega. So that looks almost the same as our pure integrator, except that we have a P instead of a 1. So this, in our real versus imaginary axis, is always on the negative imaginary line. Phase is equal to minus 90 degrees. And the magnitude is going to get smaller and smaller and smaller as omega increases. So what we're saying is, and specifically, for every factor of 10 that omega increases, the magnitude would decrease by a factor of 10, or 10 to the minus 1, which leads to 20 dB. So what we're saying is that for the high frequency part of our slope, or for part of our Bode plot, we have a minus 20 dB per decade slope, and the phase of this, as we already discussed, is minus 90 degrees. So the high frequency phase asymptote is minus 90 degrees. So if we were just talking about asymptotes, we would draw 0 degrees phase at low frequencies, minus 90 degree phase at high frequencies, horizontal line with 0 slope through 0 dB at low frequencies, and then a line of minus 20 dB per decade at high frequencies. And then what ends up happening is we just kind of fudge that curve in a little bit, and it'll work out that this is minus 3 dB right at the omega equal P corner frequency. And it'll turn out that the phase will pass through minus 45 degrees, And then it'll also turn out that the phase transition takes much longer, is a little bit wider than the magnitude transition. So that's a rough approximation of the Bode plot of a first order pole. It's also if you're paying really close attention, the first illustration of the algorithm I mentioned previously for how to plot a Bode plot. So we would start here. We would realize that we don't have a pure integrator or pure differentiator. One way to see that is to plug in s is equal to 0, and I still have a finite number. It's neither 0 nor 1 over 0. So that tells me I don't have a pole or a pure, I don't have a pure integrator or pure differentiator. I don't have a pole or a 0 at the origin. So I find my initial slope to be, and I know that my initial slope is 0, and I find my intercept, in this case, to be 0 dB. And so I would plot initially a flat line at 0 phase, and then I would just go up until I encounter a pole at omega equal to p, and then every first order pole causes my slope to decrease by a negative 20 dB per decade, and every first order pole causes my phase to decrease by 90 degrees. So that's the effect, or the Bode plot, of a first order pole. The first order 0 essentially flips that upside down and flips the phase upside down. So the magnitude, in the same way that the first order pole acts like a constant at low frequencies and then an integrator at high frequencies, the differentiator, the 0 acts like a constant at low frequencies. So this is first order 0. It also has a slope of 0, magnitude of 0, potentially if there's not a gain term. And then when we get to omega equal to p, our slope starts to go up at plus 20 dB per decade. And so that is our dB mag. And then our phase will start at 0 degrees. And then when we get to omega equal to p, we'll jump up to positive 90 degrees. And then it's got to kind of transition somehow like so. And we'll fudge the corner again like so. And this would be a plus 3 dB here. And so that's a pretty decent rough approximation of the first order 0. And so every time I come to a first order 0, my slope would increase by 20 dB per decade, and my phase would increase by 90 degrees. If this were a compound transfer function that had more stuff in it. Yeah, I think that's about all I got to say about first order terms. So that's the first 4 of our 6 building blocks. So next, let's consider the second order underdamped pole. So when I say second order underdamped pole, I'm talking about a transfer function of the form omega n squared over s squared plus 2 zeta omega n s plus omega n squared. So we're going to plug in s is equal to j omega, as we've been doing for Bode plots. For this case, though, we want to consider 3 regions. Just like before, we want to consider s much, much less than omega n, and s much, much greater than omega n. But we also want to consider s equal to omega n. And really, when I say s equal to omega, so I'm talking about j omega, s equal to j omega, where omega is equal to omega n. Yeah, so when I say second order damped pole, I'm not overly concerned with overdamped or critically damped, because those are actually cases of 2 first order poles multiplied together. So that's kind of not a big deal. We already know how to handle first order poles. Handling 2 of them is nothing special. So we're going to take this equation, or this transfer function, and write it as g of j omega, so s is equal to j omega. We still have an omega n squared there. We'd end up with a negative omega squared in this term, because j omega squared is a negative omega squared, plus 2 zeta omega n times j omega, and then plus omega n squared. So at low frequencies, we're talking about omega much, much less than omega n. So this term would be small because it's an omega, but this term would also be small. So we're going to end up with, just like in the first order case, g of j omega approximately just equal to omega n squared over omega n squared, by which we mean 0 dB and 0 degrees phase. So it starts off flat at 0 degrees phase, just like a first order term. Next, let's consider high frequencies. So omega n much, much greater than omega. So this term will be very large, and it will be larger than certainly this term, but also larger than this term, since omega squared will be larger than omega. So we're left with, for our high frequency asymptote, an omega n squared divided by a negative omega squared. So this is different from the first order pole in two ways. First of all, this is always real. So but it's also negative. That's 2 squareds with a negative in the denominator. So we're talking about something that's starting off here, and then as omega gets larger and larger, the magnitude gets smaller and smaller, but the phase, you might argue whether it's minus 180 or positive 180. We're going to call it minus 180, mostly for causality reasons. So phi will equal minus 180 for our high frequency asymptote, and our magnitude is going to get smaller. But because it's an omega squared term, if omega were to increase by a factor of 10, so what if I had omega as, say, let's say it was 10 omega n, and then it was 100 omega n. Every factor of 10 increase in the magnitude of omega would be a factor of 100 decrease. And so if I did this right, how am I thinking about this? So this would be 100 omega n squared, so the magnitude of j omega, the omega n squares would cancel. This would be 0, 0, 1. But then when I go up by a factor of 10, now I have 100 squared. So I'm going to go down by a factor of 100 instead of a factor of 10. So this is going with a slope of minus 40 dB per decade. Every time I increase the magnitude of omega by a factor of 10, the magnitude would decrease by a factor of 10 squared, or 100, and 10 to the minus 2 is equal to 1/100th, and so minus 2 times 20 is a minus 40 dB per decade. So what we're saying is that for a second order system at high frequencies, we have this minus 40 dB per decade. At low frequencies, we're flat. At high frequencies, trying to not get too specific there at the actual intersection, but we have a slope of minus 40 dB per decade. And then our phase starts off at 0 and then ends up at negative 180. And so what we haven't talked about yet is what goes on in this region near omega equal to omega n, and how rapidly does the phase transition from 0 to minus 180. And both of those will turn out, it depends on damping. So let's talk about that now. If we have j omega, or S is equal to j omega, where omega is approximately equal to omega n, or in this case, let's just set it equal, then what we're saying is that S of j omega would be omega n squared divided by, so we have a negative omega n squared for our S squared term, plus 2 zeta omega n j omega n plus omega n squared. So all I'm doing is substituting in j omega for S in my S squared term and in my S term. So originally the form for the underdamped second order system, omega n squared over S squared plus 2 zeta omega n S plus omega n squared, that's j omega, and then that's j omega squared. So that leaves me with a negative omega n squared and a j omega n here. Well, hopefully, so first of all, I've got this negative omega n squared over here and a positive omega n squared here. So those two will cancel. And so G of j omega n, I'll call it, would have an omega n squared in the numerator, and then the denominator would be a 2 zeta j omega n squared. Well, I can cancel omega n squared out of both the numerator and the denominator, and I'm left with 1 over 2 zeta j. I'm going to multiply through by negative j over negative j. I'll get a negative j squared, which is just 1. And so we're saying at resonance, we get a negative j over 2 zeta. So 1, zeta has to be between 0 and 1. So the smaller zeta is, the larger the magnitude of G at this resonant frequency. And the phase, so the magnitude of Gj omega would be 1 over 2 zeta, and the phase would equal a negative 90 degrees. So what happens is that the shape of the Bode plot near resonance depends on zeta. So if I have a really, really small zeta, I might have a really large, really sharp peak, and I might have a really quick transition. So that would be zeta, say, equal to 0.01 or something. But then I could also, I don't know if I quickly have a different color marker laying around. I don't see one. So I'll just do a dashed line thing. If I had instead, say, zeta equal to 0.3 or something, that'll be the dashed line, and this is the solid line. So 1, my peak is shorter and a little bit wider, and then my transition in my phase is also wider versus frequency. So I'm plotting this versus frequency in hertz here. So when I'm coming along and I encounter a second order underdamped pole, my slope goes down by 40 dB per decade, my phase drops minus 180, but I also have a peak that depends on zeta. And then if we were talking about an underdamped second order 0, that would flip upside down and that would flip upside down. So my magnitude would have a valley rather than a peak, and then it would go up at plus 40 dB per decade. So that is a dB mag, and this is a second order complex conjugate pair of zeros. And then my phase would go up plus 180 degrees. Okay, all of that. So now we've got all 6 of the building blocks. We know how to draw the rough effects of each of them on a Bode plot. And I'm going to stop this video here. The next video, I'll do some examples that will hopefully make this more concrete, of taking a transfer function that has multiple poles and zeros and sketching out its Bode plot. Thanks.